Thank you to SISBayes for organizing this second workshop, and I hope more will come. Thank you to Tony Canale for being the new chair and for leading the organizing committee. Thank you to all the organizing committee and to Raffaele and all the scientific committee for having me with this foundational lecture. I'm going to talk about the Bayesian predictive approach, which is really in the foundations of Bayesian statistics, but is receiving a renewed interest recently. I will try to explain reasons that I find exciting for this interest. And because I'm talking about foundations, I'm starting with foundations of Bayesian statistics to go further. I would like to take the opportunity to thank and kind of celebrate a leading figure and a maestro for all of us, for many of us, who is Eugenio Regazzini. So I think Eugenio really introduced many of us to the Finetti's work, the Finetti's predictive approach, and much, much more. Let's see how I go to the next slide from here. No, it's okay. Yeah, here is Eugenio with other maestri, with un'intrusa, with Percy Diaconis and Michael Jordan. Also had, we know them. That's a photo in the conference, at the conference in honor of Eugenio Regazzini in Pavia in 2016. And there is another person that I would like to, devo farla qui? And that I want to thank is my colleague and friend Sandra Fortini, and what I'm going to tell you is based on joint work with her. So inferential approach, we are used to the, predictive approach, we are used to the inferential approach. What do I mean? Well, I think we are all familiar, at least since Leo Breiman provocative paper in statistical science, with the two cultures. Classic statistical inference versus algorithmic prediction. Little parenthesis, I think we all read that paper, but in the discussion by Efron says, well, where is causality here? So I'm not talking of causality, and I think it's great that Guido gave that beautiful lecture yesterday on causality. And I'm not talking about this, but just of these two cultures, inferential statistical procedures versus predictive algorithm. And we are aware of that debate, say, the more so nowadays with statistics and AI. And the Bayesian approach has prediction in its foundation. So I think the idea is it might be combine naturally both these approaches. That's kind of the idea of the lecture. So in classic inferential setting and prediction. So in classic statistics, prediction is done by patiently statisticians study the phenomenon of interest, formulate a model, specify a model, and then from the model have prediction. In Bayesian statistics, we specify the conditional density of x1, xn given theta. Theta is treated as random, as a prior, and we compute the posterior, and then we compute the predictive distribution as we know. With full Bayesian uncertainty quantification. This is good. However, specify the model may be demanding, eliciting the prior may be difficult, especially if we have big black box models where parameters lose interpretation. How do we specify a prior? Well, with ideas of shrinkage and so on, but still. And especially computations may be overwhelming, especially if we have data that arrive sequentially, streaming data. So even our Markov chain Monte Carlo is not enough. We have to do sequential Monte Carlo or other things. And then I have to say that computation, so the urgency of having Bayesian procedures that were fast, scalable, the time was machine learning, the urgency from machine learning was my motivation for looking at some perhaps simpler approximate procedures, maybe not fancy MCMC, to speed up computations. Indeed, on one hand, we have this solid and very valuable statistical inferential setting. On the other hand, we have, but slow in computation. On the other hand, we have a wealth of predictive algorithm. What do I mean by a predictive algorithm? Will be a strategy to provide prediction that with no explicit model or prior, just a strategy to provide prediction. So these algorithms perform well, work well. Usually they do not have a clear understanding or uncertainty quantification, but work well. And so this talk will be a review of the predictive approach, but I have a sort of a guideline aim, which is to show that by taking a Bayesian predictive approach, we can look at these fast, well-performing predictive algorithms as Bayesian predictive learning rules, predictive rules. And then we can say, is this predictive algorithm implicitly using a model and a prior? Because if so, then it's natural to give posterior, as we will see, and so have full uncertainty quantification on the algorithms. Applications, examples and applications are many, both in statistics, where this kind of procedures may be proposed as approximation, faster approximation of a expensive to compute Bayesian procedure, or in machine learning and AI. For example, I think there is exciting work by SISBayes. I'm started working on this, but it's too early for a talk. The problem of understanding how in context learning in large language model works. Is it any Bayesian? Is it martingale? Well, Chris Holmes says no, but still. How trained transformers work. So if it's early for me to tell you about what we started to do with Susan and others, but if you want to see something more, you may look at Susan Weiss' talk at the recent post-Bayesian workshop. It's called like this, at UCL last May. It is recorded and you can find it online. I think it's a beautiful for me and a kind of intriguing talk. Instead, my examples will not be this too early, but what I will try to do, the content is, I have to start from foundations, like it's called foundational lecture. So this, I hope to be quick enough in the first part, because to the audience, those things will be well known, but I didn't find that I can skip them. So basic concepts, the basic notions of in the predictive approach, to go to kind of a weakening exchangeability, asymptotic exchangeability, and predictive algorithms. So we will go from a predictive rule, from an algorithm to a predictive rule, and I will try to say how to get to the posterior and have Bayesian uncertainty quantification. And then the third part of the work will be directions, ongoing work, and open problems, for which we have some results. But okay, so basic of foundations of Bayesian statistics. The foundations are Bayesian statistics, as we know, has decision theoretical foundations, where we imagine we have agents that have to take decision, have to act under uncertainty or incomplete information, have to evaluate risk and so on. So that's a different setting than having to face replicates of experiments, the classic frequencies. And in this framework, in this decisional setting, the principle is that probability is a prescribed tool to formalize the uncertainty, to formalize incomplete information. Maybe a strong principle, but I think that's the principle. And should be expressed, and probability is the prescribed tool to formalize uncertainty, and should be assigned on observable facts. So the modeling effort is to elicit the probability on the joint of the X on, say, the observation, X1, Xn. Please interrupt me if I'm not clear. So we have to assign the joint because we reason on the X. Then how do I assign P of x1, xn? Well, we may use models, and models are valuable, whatever. They can bring really important information, but have to be thought just as a ring of the chain that goes from the past to the future. So we can instead, in a completely predictive, say, approach, by reasoning directly on the predictive, possibly bypassing models and priors, and assign the joint as a sequence of conditional. That's the idea of the predictive approach. Try to reason directly on prediction to assign what the object of interest. In fact, I said that the conditional, one step ahead conditional, the predictive, because we are going to use a lot this idea of Bayesian predictive rule. What is a Bayesian predictive rule? Again, in the foundations, we have to think of the foundations to understand it. Well, I said probability is the principle to formalize uncertainty. And because information probability is expressed through probability, it follows that learning, a change of information learning, is expressed through conditional probabilities. That's the other principle that follows. And the predictive distribution, I will denote by Pn, formalizes how we learn on the next observation given the past. It's not the true mechanism that generates xn plus 1 given the past. It might converge to it, it might learn it, but it is not. It's our probability on, so our information of xn plus 1 given the past formalized through probability. This is going to be important. And any predictive rule in this sense is Bayesian. Doesn't need to be exchangeable, it's Bayesian. So the predictive distribution, of course, gives, ragazzi, sono CTRL L. The predictive distribution, as I said, gives the joint, and if you have it, if we have the joint for any n, we have the finite dimensional distribution of the process xn of the sequence, so we have its probability law. And indeed, this is the content of Ionescu-Tudskaya theorem. So if we have the sequence of the predictive rule, we assign the probability law of the process of xn of the entire sequence. So we can assign the probability law of the process through the sequence of predictive distributions. All familiar, yes. So we are free in assigning our predictive rule. It's a set of conditionals, no formal constraints, but some natural desiderata. Let me say, I will be in the context of random sampling all over the lecture. What is the first basic desiderata? The predictive is a way to convey our information on the future given the past. And if we have random sampling, independent replicates of an experiment in the same conditions, well, it's natural to think that the labels do not bring any information. And so it means that the order doesn't matter, that the joint is invariant under permutation, so exchangeable. And if we have a sequence, we ask this invariance under permutations for any finite permutation. And so we say xn is exchangeable, the sequence is exchangeable. Not needed, Bayesian doesn't need to be exchangeable. Sometimes I have this objection. No, it's a natural desiderata for the predictive in random sampling. Another important fact is that we are free, maybe we are exchangeable, but our predictions are here and the empirical is there. That's not good. So another minimal desiderata is to require that the prediction and the frequency will become closer and closer with probability 1. And then we are used to inference. So in this predictive story, where is inference? Is there any link? In other words, Pn, our predictive rule, that is going to be an algorithm, is implicitly using a model and a prior. Because if so, then this model and the prior have a predictive justification, but also we are back in the usual familiar inferential setting. So we want to reason in predictive way. We specify Pn, the sequence, the predictive rule, but we want it to be exchangeable. And then we have just to check that the predictive is invariant, where the predictive is a joint divided by another joint. The joint have to be invariant. So the predictive should be symmetric in the future and symmetric in the past. And this is if and only if this is exchangeable. Then if we have exchangeability, that other minimal check, frequency and prediction, holds. Both the Pn and the empirical converge to the same limit, which is a random f. I will use the tilde to underline that it's random. This is also a property we are going to use all the time. The limit, so the frequency and the prediction will converge to the same f. And this f is random. This f is going to be our model because the third property we want, link of inference, well, is given under exchangeability by the Finetti theorem. That's the role of the Finetti theorem for statistician or Bayesian statistician. Because it says, well, let me phrase it informally. If we have a predictive rule, exchangeable, then implicitly we are using a model and a prior. The model is the limit of the predictive or of the empirical is the same, and that's what is written there. So again, in a predictive approach, we can directly move from the predictive assumptions on the observable, and then if it is exchangeable, characterizes by the Finetti theorem a model, the limit of the predictive, and a prior. The prior is, the limit is random as a distribution, and that distribution is the prior. Familiar to everybody?
Assign us a sequence of the sequence of predictive depend on parameters.
No, the predictive distribution, the first slide, is integrated out. The parameter is.
You want to call it hyperparameter.
There is no prior, no? So no. I have integrated via. No, it is a question, but that's another talk. We can go back to that. But the story is. You have, if you have a prior with a hyperparameter, you give a prior to the hyperparameter, integrate out, and then you have a prior with no hyperparameter. Yes.
How to set? Let's call it hyperparameter to understand. This predictive should depend on some parameter, right? There are no numbers. Depend on some parameter.
I will have
a method of some way.
Yes, it is in the example. I think it's in the example. That is, but it's a good question, Raffaele, but let me return on it in this example, and we'll go back because it's a very important question. Anyway, the fact that we can characterize model and priors through the sequence of the predictive distribution, predictive characterization is not new. It's a long tradition in Bayesian statistics. Think of Diaconis and Ilvisacker characterization of conjugate priors for the exponential family, or Polya sequences, Blackwell and McQueen. We specify a predictive distribution that is a weighted average between initial P0 and empirical. That's very natural, weighted average between the empirical and P0. There are parameters, you see, there is this alpha, but for the moment, alpha is specified. I return on that. And the sequence is proved to be exchangeable, and as the Blackwell and McQueen show, the predictive, they show, no, the predictive, the predictive converge to F, and F as a prior, which is a Dirichlet process. Okay, so nothing new, it's a long tradition. And also, I think there is another fact. I said that the basic desiderata, but I didn't say another desiderata, that you can do computations. If I have to specify the predicted distribution directly, instead of giving a model integrated out the parameters, I am encouraged to be fairly simple, analytically and computationally. And indeed, that's one of the beauties of the Dirichlet process. The predictive is so simple, but if we want exchangeability and tractability, often it's difficult or even impossible. For example, if we have continuous data, we may want to smooth the empirical using a kernel or something. We break exchangeability. And we have to use mixture models, and then computations are complicated, and with sequential data even more. So our idea is to accept an approximation, to accept specification predictive rules that maybe break exchangeability but are simpler to compute, and but still approximate exchangeability at least asymptotically. For n large, they are closer to an exchangeable procedure. Okay. As I said, exchangeability implies that Pn converge to F tilde, a random F. The reverse is not true, but there is this result in Aldous, the lecture notes of Aldous from the Saint-Fleur Summer School, the Bible on exchangeability, that says that if Pn converge to a random probability distribution, then Xn is asymptotically exchangeable. There is a formal definition. Informal, it means that for n large, approximately the Xn are conditionally IID given F, and this F, so we have again approximately an exchangeable setting with the model given by the predictive and the probability law of this F given by the limit of the predictive and the probability law, which is an implicit prior. Moreover, I think Pietro Rigo in several work about informal, but this paper on PCD and Walker, it's also proved that F is still also the limit of the empirical. Good. So the idea is now, if we have a PN, which is maybe a fast predictive algorithm that has some vague idea of being Bayesian exchangeable, but it's the rule. We use an algorithm that's a rule that we use to predict. Well, that's a Bayesian predictive rule. I said, if I have a rule to predict expressed through probability, that's Bayesian. So I take the algorithm as my PN, and then if it is asymptotically exchangeable, if it converges, then I have a model and a prior. A model as the limit and an implicit prior. But question, how can we assign a predictive rule that converges? And also, how can we get a link to parametric model? I'm being non-parametric in the sense that being general. Predictive rule converge to F. This F could be expressed in a parametric form, but where is the link? And also, how can, once we know that, oh, good, we have a model and the prior, how can we compute the posterior if we don't have the prior? Because the prior will always be only, usually it's not available explicitly. So that's the first. How can we assign this convergent predictive rule? We may use a sufficient condition. An important sufficient condition is that Pn is a measured value martingale. In other words, this is equivalent to say that any future observations, n+1, n+2, n+, are conditionally identically distributed given the past, CID, a notion developed beautifully by Berti, Rigo, Fratelli, and others. Indeed, there is a theorem by Kallenberg that says that a sequence is exchangeable if and only if the predictive is a martingale and the sequence is stationary. So if we only use a predictive rule that is a martingale, we break stationarity. Time matters. The order of the observation in the first part matter. But then they converge, and so after a while, we are back almost to exchangeability. The order no longer matter. I return on this if I have time. Yes, but how to specify a martingale? Well, there are examples in literature and growing literature, but on the other hand, as I said, there are many, as Chris also says, no? There are many predictive algorithms out there. We can look at them and read them as Bayesian predictive rule. This is, as I said, the predictive algorithm may be what I'm going to show, a strategy for computation, an approximation in statistics, or they can be ChatGPT. After all, large language models provide a predictive rule. No, they could provide a prediction on the next word or phrase or whatever. And there are trained transformers that are trained to behave as a Bayesian, but not exactly a Bayesian, maybe an asymptotically exchangeable Bayesian. So It's not such a crazy idea. And this is my classic example. I have two examples that I always make. Mixture models, because we had a lot of mixture models. Consider the popular Dirichlet process mixture model, where we have a mixture with a mixing G. G as a Dirichlet process prior. And we were interested in estimating G, but data arrives sequentially. So we have to estimate G, run our MCMC, but now we have a new observation and a new observation. And so MCMC is hopeless, and we have to use maybe sequential Monte Carlo or big data variational base. There is something on sequential variational base, not so much, but there is. But here is also a convenient, simple recursive algorithm that says, okay, let's try to propose something that is faster and works simple. Start from an initial G0, and then for every T, we update our estimate, our initial G0 as a weighted average, oh my God, a weighted average between our previous estimate. And what is this? This is the posterior of theta using the previous estimate of the prior, but incorporating the new observation. And the step n, this Gn, is the proposed estimate of G. That's called the Newton algorithm in the Bayesian non-parametric literature. However, where is uncertainty? Now we have an algorithm to compute an estimate, but where is uncertainty? And also, is this any Bayesian? We have this updating rule. Well, take the idea that I discussed so far. We can read it as a Bayesian predictive rule. So suppose we take it seriously, and then we say, well, this is in terms of theta. What happens? What are we doing in terms of the x, the observable? Well, we are basically using a predictive rule that depends on Gn. And I don't know if I'm a bit bad. No. That depends on Gn. So we plugged that Gn in because we said that we have a mixture. We plug this Gn in. And so we have an updating rule for the predictive. It's a weighted average between the previous predictive and the predictive, where the mixing is the posterior from the prior Gn minus 1 given the new observation. Are you with me?
Yes.
But then we have a predictive rule, a recursive predictive rule. And then this is a Bayesian predictive rule, because I said the Bayesian doesn't need to be exchangeable. That's the strategy on which with which I learn. So it's my predictive. It's expressed through probability, yes. So Bayesian. And then is it implicitly using any model and prior? Well, we show that it's a martingale, sufficient condition. And then Pn, we can compute its limit. We show that the Gn converges to a G tilde, and then we can compute the limit. And the limit is a mixture with this random mixing. So for n large, so the model is asymptotically exchangeable. For n large enough, then we have a kind of an exchangeable mixture model, approximately. X given G has a density, and G has an implicit prior. It's not a Dirichlet process. We also prove that it, under very general condition, it selects an absolutely continuous distribution with probability 1. So it's a new prior. Anyway, and we can do the computations because we started from the algorithm. The prior and the posterior, well, the prior remains implicit, and also the posterior remains implicit, but we want the posterior, otherwise where is the advantage? It's just a cultural interest, but we want to provide, because we are back in a Bayesian setting, we can give all the beautiful Bayesian full uncertainty quantification. And that's what I'm going to tell you. We will approximate the posterior, although we don't have the prior. Another classic, we always do these two examples. They are examples in the paper with Sandra on statistical science published last January. That's a review, so then I will write it. And so basically the talk uses material, and if you want to go back, that is a reference. So another example, suppose we have to classify items 0-1 classification, and we have items that arrive sequentially, and we express a probability that yn is 1 as a function g of the features xn and the parameter. G may be complex, maybe a neural network, so computations are difficult. What people often do is, given a training sample, it's common to estimate beta minimizing a loss function. The loss function that expresses the discrepancy between the actual values or the values predicted at the model and the actual values. Observation arise sequentially. And computation can still be difficult, but and the popular recursive algorithm for this aim is to use is the online gradient descent that is starts from beta 0 and updates beta n, previous beta n, plus an appropriately chosen update along the gradient. So for example, for simplicity here, we consider a logistic regression and the binary cross entropy loss, and that's the expression of the updating. So again, we have a sort of predictive algorithm in this, the sense that then we plug at time 1, we have the predictive of yn equal 1 depends on beta 0, beta 2, no? We have this. Indeed, we can read this story as a Bayesian predictive rule. Well, to be more formal, we have pairs. So here is a random regression, random. So both xn and yn are random. We take them as, if you take them both as random, and we, for a moment, for simplicity, assume that xi, iid with some px, the marginal, then we have a joint predictive for the next pair. So we have again a sequence of pairs, xn and yn, and we can, this pn, the joint, is such that the predictive, the joint is the predictive of xn plus 1 by the RIIDP, and then the predictive of yn plus 1 given the data n xn plus 1, and this is 1. So we have a joint pn, it's bivariate, but x in my previous slides could be multivariate, whatever. And then we show that under the general conditions, in this beta n given by the online gradient descent converge to a random beta, and you can imagine if this G works well, then Pn converge to a random F tilde, and this random F tilde is such that its condition is Bernoulli. So basically we have a Bayesian exchangeable setting, Bayesian setting where yn given the feature and beta is Bernoulli, and there is an implicit prior on beta. Moreover, this beta n can be read as the posterior expectation of the unknown, the random beta given the data, which is something that we always have in the under exchangeability.
So it's xn, it's xn, it's xn, Bernoulli xn.
Oh, yes. Yes, typo. Thank you. Yes. I think, well, it can be yn plus 1, xn plus 1. I think it should have been, yeah. Thank you. So again, any question? Making sense? Completely lost? Sleeping? Okay. Well, we can make Bayesian inference on beta without the prior, but to make inference, we need the posterior. I didn't tell you anything, so for the moment, on how to approximate the posterior, so I'll go back to this. So how can we assign a convergent predictive rule? Formally, well, there are many examples. For example, using a martingale, or taking from other literature predictive rules. But where are the links with the parametric models? I said Pn converge to F, to a distribution. That's a general formulation. That distribution could depend on parameters. And so we want to see link with parametric models. And indeed, in the examples that I think the examples are kind of cute because they have so many aspects. In the examples, the model that generically I denote by F tilde, the limit of the predictive, which is also the limit of the empirical, is a random distribution, F tilde. But in the examples, if you think in the mixture example, the DP mixture, the limit is a model indexed by the mixing distribution. The parameter is infinite dimensional, it's a mixing distribution. The limit was a mixture with random mixing distribution. That's a parametric model, semi-parametric. In the regression example, in the logistic gradient descent, we had a model indexed by beta, parametric. So the story is, in general, Pn converges to an F. But this F may be a parametric form. And then we are back to parameters, familiar parameters. In parametric models. So a general procedure could be, well, under exchangeability, the parameter of a model, at least in basic random sampling setting, is the limit of predictive sufficient statistics. For example, limit of the empirical, if you think that the sample mean is enough to prediction, the sample mean converge to the population mean. That will be my parameter. Well, no, under condition. So this inspires the following specification. So we want to get to a parametric model. So we say Pn is a predictive sufficient statistic, sufficient summary of the data that is sufficient for prediction. And so, and Pn, the predictive, there is a little bit of abuse of notation, but doesn't matter. The predictive is a function, only depends on the sufficient statistics through the form f. So is a function f to be parametric. I kind of also saying what is this. I want to get to a parameter. I also say what is f. Is a function f of a predictive sufficient statistic. I denote by ftn. And then tn is updated recursively as in the algorithm as tn of the step before, alpha n and a sort of a loss function, tn minus 1, and the next observation, updated with the next observation. Under conditions on which I will return, tn converge to a random theta. You might guess that's a martingale structure for tn, but they say under condition tn converge to a random theta, and then this predictive rule, say it's continuous uniformly in X, this predictive rule converge to an f theta. So we have a parametric model for n large. We can say xn given theta, IID, f theta, and theta is an implicit prior. This is related, Walker is always brilliant at this idea somehow. I call it plugin predictive in the sense that Fong and you have an archive paper, I think it's, they study kind of asymptotic properties of these plugin predictives where Tn is directly the MLE. So this, what I called a predictive sufficient statistics, a kind of more general, maybe just the MLE. And they start, well, it's very close, that's somehow a bit more general. Okay. So somehow I gave you an idea, at least an example where we can have a limit that is parametric. So we can go back to a parametric model or semi-parametric. But now how can we approximate inference not having the prior? Because I never said what's the prior, and usually you can, it's a really difficult also in the probabilistic literature, except some important cases is not explicit. Well, we don't have the prior. We have the predictive too. We have the predictive, but we don't have the prior. How can we compute the posterior? We have two strategies. We can sample from it, or we can give a Gaussian asymptotic approximation. These are the two strategies that are available at the moment. We can sample from it through what I call predictive Monte Carlo. In the paper by Fong, Holmes, and Walker is called the predictive resampling. Are you all familiar with it? No, so I'll tell you something quickly. We proposed that in our 2020 paper, but that's developed much further and with more examples in Fong, Holmes, and Walker discussion paper. Well, I will show also this asymptotic Gaussian approximation that I anticipate are not Beston-Fomisis theorem, and for some reasons that I'll kind of quickly explain. They are kind of rather, we call it dupe PVM to understand, to be quick. I will show. So predictive Monte Carlo or predictive resampling. Suppose we are now, let me stay in the general case, Pn converge to F, a distribution. Interest is in inference on F. To start with, let me say we have an income distribution. We have an unknown income distribution F. We are interested in estimating F of T. T is the poverty threshold. We want to estimate the proportion of people under the poverty threshold. F of T, or we may be interested in estimating functionals of F. For example, the mean, unknown mean. So we can design a predictive Monte Carlo or predictive resampling algorithm to sample either from the prior, because we might be curious what's the prior, and or from its posterior distribution. I show you how to sample from the posterior. Remember that, well, suppose we have data x1, xn, we have the predictive, it's a strong, we have the predictive, then we have x1, xn, and then we can generate also the future observation. We can generate an entire sample path in principle, which is a little omega. And we said the limit is F is random. It's random is F of omega. If I see the omega, I know F. So of course we cannot generate an infinite sequence, so we truncate and we have x1, x capital N. The first piece are the observed data and the other are imputed, are generated from the predictive. And then if N, capital N is large enough, that's a bit like the entire sample path. And because the empirical and the predictive converge, we can, well, in principle, if I have the entire sample path, F tilde is random. That is a function of the little omega. I know I have the little omega, I have its value. Okay, that's approximated because it's truncated. I cannot, but suppose it's 10,000, whatever. Then I can take the empirical or after capital N, or I can take the predictive. They will be close to each other and they will be close to the limit. So I take I take Fn or Pn roughly as a sample from the posterior, because x1, xn is fixed. If we are interested, then I repeat m times and I have a Monte Carlo sample, proximal Monte Carlo sample, because the sequence, in principle, I can generate omega 1, omega 2, have anytime a realization from the posterior. Example, if I repeat the same story m times, I have a Monte Carlo, proximal Monte Carlo, up to the truncation from the posterior. If I'm interested to a functional, then I can compute the functional at each iteration where this is, and so anyway, if I start from n equals 0, so no sample, I have a sample from the prior. Okay, now you were looking. To? So this is what we do there. And if the predicted distribution is empirical, because we are allowed to use the empirical directly as is not exchangeable, but it converges, so we are asymptotically exchangeable. If we take as a predicted directly the empirical, then what I described is Bayesian bootstrap, parametric Bayesian bootstrap, as developed by von Gomes and Wolf. Sorry? The predictive Monte Carlo. So remember that Pn converge to a random F. The distribution of this random F is the prior. If I have x1, xn, still it converges, but the distribution of its limit is the posterior. If it's easier, you can imagine that n equals 0. Then you would have a sample from the prior. So I say, what does it mean that Pn, the empirical or the predictive, they are a function of x1, xn? It converge to a limit. This limit is random. It's random because it's a function of what we observe. With a sample path, the limit will be this distribution. With another sample path, will be another distribution. It's a very good question because it's unusual under IID data, the limit is not random. So it's a big different conceptual frame. But you didn't object why the limit is random, and I went on. So you guys, I mean, and so if 5 minutes or so, if the limit is random, it means that depending on the sample path, I may have a distribution, a sample path, another distribution. But then if I can generate those sample, and then all this distribution design a prior or a posterior if I condition on the data. So if I can generate a little omega, if I can generate a sample path, then I have a sample from that posterior. I generate another, so I have a Monte Carlo sample. And this is what is done here. So I generated the sample path. If I have data, I generate, but the first are fixed, and then I generate all the future observation. So I have the little omega. And I can compute, well, I have to truncate, but the idea is, suppose that I have a long trajectory that is more or less the entire sample path, then I have a limit, a sample from the posterior, or the prior if I have no observation. And then I repeat, and I have many samples from the posterior, or from the prior if I start with if I consider n equals 0. So I have a Monte Carlo sample up to the fact that I truncated from the posterior. And that's different from MCNC. It doesn't require any MCNC, but there is ongoing work on how to accelerate this resampling. But we have the predictive. This can be done also with exchangeability, but we need the predictive. But also it's interesting to have analytic approximations. For example, in the logistic example, we should sample pairs because our X now is bivariate, multivariate, X features and Y, but we don't have the distribution of the X. So we cannot use this predictive sample because I suppose the XI, IID, but I don't want to use PX because we don't know it. So analytic approximations are interesting. Analytic approximation of the posterior distribution, and they are also used for accelerated predictive resampling or predictive Monte Carlo. It's other work by also others, by Fong and Yu and so on. So let me consider again the general case, kind of F is an unknown income distribution. I consider here only the case where Pn is a martingale. Suppose interested in estimating the proportion of people under the poverty threshold T, so just f of T at a given T. Again, remember that F, the unknown F, the model is random because it's the limit of Pn. So if we have a finite sample, we don't know the limit yet. We don't know that's another change of perspective I'm trying to convey in this last few minutes. So the uncertainty that is left is due to the fact that we have a finite sample and we don't know the limit yet. When we think of the uncertainty in the posterior distribution, in principle, we shouldn't think of uncertainty around the truth at F0. I never mentioned the true F0. I'll go back to this, but it's just a predicted converging to a random F with a prior that comes from it. So the uncertainty that we formalize in the posterior is describing the fact that we are uncertain about the limit of Pn. Fong, Holmes, and Walker call it the missing observation. If we have all the sample path, we know the limit, but we have only a piece. Well, the uncertainty is due to the fact that we don't have the future observation. So intuitively say, I said that F tilde is this random F. This random F is the limit of the predictive. I have x1, xn, I don't know the limit. But suppose that I know that the predicted distribution converges very quickly. If I have n equal 100, I will be already pretty sure about the limit. So the distribution, the posterior of F, will have a small variance. Although it is after 1 hour talk weird, Is it clear enough? So the uncertainty is about the limit. If I know that it converges quickly, I will be, even with just 100 observation, I will be pretty sure the posterior variance will be small. So no surprise, intuitively, so surprise, because that's not the way we think of it, but we can go from the predictive distribution, although we don't have the prior. We take the predictive distribution and we approximate the posterior, asymptotic Gaussian approximation. Asymptotic Gaussian approximation, the mean is the predictive. The variance will go to zero, that's Doob theorem, or the Finetti theorem itself. But how? What is the expression of that variance? How does it go to zero according to a normal error? That's here. So we consider, so we say the posterior uncertainty depends on the way the predictive, on convergence, say, on the limit of the predictive, blah, blah. So consider the Pn converge. Consider these predictive updates. Pn minus 1, the delta. Of course, this delta go to zero because the predictive converge. But how it converge? We want a variance. So let's consider that Vn that depends on the delta go to zero. So let's take them square. So we consider that expression and can show that asymptotically the posterior of f of t is normal center on the predictive distribution because that's we know this, with a variance that is expressed in terms of the predictive updates. This is true for almost all the sample paths. P is the probability law, say exchangeable or asymptotic exchange probability law of the sequence. So for P almost all sample path, the posterior, you see this is a function, is approximated as a normal with that mean and that variance. It's not a BVM result because the BVM result would be for P, F true, infinity, almost all. Okay.
Once or twice.
This is only 4-pointwise, and also this Vn is a function of x, so we can use it to compute I will return credible intervals, and then we see that the Vn depends on, so that the expression of Vn really says if it converges quickly, then we have small variance. But the variance may be too small. So suppose that Pn is equal to the initial degenerate case, extreme case. Pn is equal to P0 for any n. It converges immediately, but it doesn't learn from the data. So the issue is more subtle than just looking at the convergence rate. We should also look at the learning rate, because the predictive changes because it's learning from the data. It changes because it's learning from the new observation. So we have a convergence rate and a learning rate, and we should balance them. So maybe let's look at this example. That's exchangeable Dirichlet process, the Polya sequence I mentioned. I write it in a recursive way, and then at the delta update, if you see, are a function of that alpha, Raffaele. That alpha, how do you choose it? No? This alpha, let's say if alpha is large, as we know, if the delta will be small, it's in the denominator, will be small. And so it means that if you use a large alpha in a differential setting, we would say the prior has a bigger role. Here in this predictive understanding of things, we say, well, if alpha is small, we don't learn much from the data. The predictive is not sensitive enough to the data, not enough. It doesn't learn much. And indeed, if we do a little simulation from a true distribution that is a beta, from a true, if I do simulation, frequencies or beta, we have a true, and we'd better learn it. So I think I'm Bayesian enough, but frequencies properties are also important. So if I look at that is the credible band. So these are marginal credible interval, T by T. So, but that's a credible band. It's good coverage, I would say. It includes the true. Alpha is 1. But if I take alpha large, I don't learn much from the data. And if you see, it is more narrow, but also it doesn't include the truth. So it's a balance between predictive convergence, predictive rate, convergence rate. I would like to have a fast convergence to get to, but also I would like to have a good learning rate. I have to balance the two things.
But in a way, you don't center your interval well.
So there is a bias and there is a variance. Both the issues are there. So I think from this on, I had kind of ongoing work, but I think I will go very quickly only on this. So I think there is an issue, as I kind of mentioned in the last GMP in an understandable talk. There is an issue of predictive efficiency. Now, that's a foundational lecture, foundational things. In frequentist statistics, we have a notion of inferential efficiency. Efficient estimator, biased, Fisher information, variance, inverse of Fisher information, efficiency, inferential efficiency. Here I try to be predictive. So can I give a notion of predictive efficiency? Is there Guido? Is there a notion of efficiency in Bayesian statistics, Brunero? I don't know, not in the sense of Fisher information. I think the reason is that I am ignorant, but if I think of optimality properties, I would think of a decision setting. Loss function, optimality, and miscibility, that's another story. Or I would think of what people do, scoring rules, loss, calibration, this other literature. I'm not there. I didn't look at that, but I think it's a very genuinely Bayesian predictive criteria. Here I just said, can I give, and that's somehow Raffaele's question, how do I choose that alpha to balance a proper convergence and learning rate? I would like to find predictive conditions, so conditions on the learning, on the delta predictive updates that ensure a posterior variance such that the credible intervals have good coverage, because if I have a true, so to close and I skip, so that's why I say, well, these are BVM results. That's my idea of efficiency in the narrow, if you want, but I think intriguing enough vision. I would like to find conditions. So what we have is first we look at the parametric case where we have a parametric setting based on Fomisis. I consider the construction with the sufficient statistic, as I mentioned. We have BVM saying like this, and then you see that if you see it's up there, the posterior is a center on Tn, but the variance, the rate is Bn in best and Fomisis theorem. That would be 1 over n. This is lower unless we calibrate well that alpha. Or also the posterior variance is related to the loss that we use in the update. And so we have a choice of the loss that guarantees that U theta is called here is actually the inverse of Fisher information. So we have a statement that now has a center and Fisher, the variance of the efficient estimator as in BVM. And this is something that again Walker, Holmes, Walker, Fong, and Yu considered, maybe not because it's kind of natural to correct the update. So even in the example of the online gradient descent, that is a bit brutal. That's a bit like an example, but we should correct with this adding the score and Fisher information in the updating. Okay. Then this is a comment that I already did. I think other directions are multivariate, in particular in this kind of parametric setting. Stefano was asking, is this only for T? Well, it can be extended for T in a grid or also for the entire process. And this is just the slide to say, yes, we have a theorem for T and then also for the entire process. Entire process is interesting because if you want the posterior functional, we can, but this is again a bit of we have the results, but not an archive yet. And also this is skip. This all is said in under exchangeability. I mean, in random sampling. Sorry, extensions. So there are some extensions from people, but I think say just fixed design regression. We have regression is the most important problem. Either stochastic design, that was that example, fixed design, which is basically partial exchangeability. Fong, again, you and others have done something. We just, I think, we are not there. We have this notion of partially CID that maybe can be done. Thank you very much.